All right. So thanks everyone for being here. So this short course is an introduction to GeoChemFoam with a focus on how we use it for pore scale modeling in porous media. So I'll give a brief overview of OpenFoam, explain what GeoChemFoam adds on top of that framework, and then walk through a few example cases that show how we can go from images to flow and transport simulations. And the goal is not to just show you the software, but to give you a practical sense of how it is structured and how you can start using it yourself. So as I just said, here's the plan for the session. So we start with OpenFoam. Then I'll introduce GeoChemFoam itself, including where to find the code, the documentation, and community resources, such as the GitHub repository, wiki, and discussion forum. After that, I'll give a quick tour of the source code and tutorial structure, because understanding how the cases are organized is really important if you want to modify or extend them. And then we'll go through 3 example applications. First, single phase flow and transport in the Ketten case. Second, multi-phase flow and relative permeability in a micromodel. And third, multi-scale Darcy-Brinkman-Stokes flow in an Estioletta sample with multiple phases of microporosity. So before getting into GeoChemFoam, it's useful to understand what OpenFoam gives us. So OpenFoam is not just a single solver. It's a broad toolbox with hundreds of programs and libraries that cover pre-processing, solving, and post-processing. And on the pre-processing side, it includes meshing tools like block mesh and snappy hex mesh, as well as mesh conversion utilities for bringing meshes in from other packages. And at the core are libraries for finite volume discretization, parallelization, transport models, and many other physical properties. And on top of those libraries sit the solvers, which can handle a wide range of physics problems, including incompressible and compressible flow, heat transfer, and many others. And then once the simulations are complete, OpenFoam integrates well with peer review and other post-processing workflows that we'll see today. And GeoChemFoam builds on this ecosystem specifically for pore scale and multi-scale porous media applications. So at the pore scale, OpenFoam is particularly useful because it already contains many of the ingredients that we need, right? For example, we can solve single phase flow using the Navier-Stokes equations. And if we're using GeoChemFoam, we can solve scalar transport using advection diffusion formulations. And we can also use the volume of fluid methods to solve two-phase flow. So you can see here, this is the streamlines of the velocity profile going through a piece of Ketten limestone. So, the flow is going around the grains, and you can see it's not just a straight line going through rock. There are many tortuous paths that it has to take. And so this is the transport that follows those streamlines. So we can see if we inject a species from the left, we can slowly, the species propagates through the rock to the outlet. So this is what we're going to go over in the first tutorial. And then here, this is the second tutorial. So it's injection of a non-wetting phase into a micromodel. So we've got potentially, you can give these it's a numerical model, so you can give whatever properties you want, but in this case it's oil injected into a water-filled micromodel, and you can see how it spreads. And so GeoChemFoam, I'm giving a brief overview with a couple of different solvers today, but it goes beyond just reactive transport and alone. And it's targeted specifically at flow and porous media. So it comes with a lot of scripts that OpenFoam doesn't come with. If you're ever taken an OpenFoam course, the first thing you do is go through a very painstakingly creating a mesh and then setting up the flow simulation and running the flow. And we've put a lot of scripts on top of that to make that much more easy and manageable. And this is important because in practice, a lot of the challenge is not just the physics, but also setting up cases efficiently and reproducibly. So we spent a lot of time developing that workflow for the most common cases that we think people are likely to encounter. And there's also a pre-compiled Docker version, which is very useful for getting started without worrying about how to install the dependencies. Although the full source code, if you're interested, is available on GitHub. So the code is intended to be accessible, modifiable, and usable by the community. So our first example today will be the Keton case. It's tutorial number 1. And the objective here is to take a micro-CT image, convert it into a computational domain, so mesh it, and solve for the flow field and then solve for the species transport. And this is a nice introductory example because it captures a common digital rock workflow from image to simulation. And the commands show, or the equations shown here. Sorry, no, this is, there's some commands here that illustrate where the tutorial lives and how to copy it into your run directory. But we'll go more in detail of that in a little bit. But in terms of physics, the flow problem includes inertia, pressure, and viscous stresses. And while the transport problem includes advection and diffusion. And this case also gives us useful dimensionless and flow-related properties, so over here, such as the Darcy velocity, injected pore volume, Reynolds number, and Peclet number. So it is a compact example that links geometry, flow, and transport in a very direct way. So we're going to run through this tutorial as is, and then we're going to decide as a class what we can do to interact with this tutorial, right? You don't necessarily want to just run the tutorial. You want to, maybe you want to run it on your own image. Maybe you want to use a different meshing or change the flow direction or the flow rate and pressure, or maybe change the species that are going through, change their molecular diffusion coefficients, add another species. So we'll do one example, just clean as the tutorial set up, and then we'll change something and look at how the results differ. So with that, I'm going to attempt to share my other screen. Okay. So here we are on the left on the GeoChemFoam website. So it's just github.com.geochemfoam, and then there is a GeoChemFoam base source code. And so you can see here, there's links to the source code, precompiled Dockers, but what we're interested today is the users wiki with tutorials. So in the users wiki, we have all the instructions, which should have been sent out to you before class about how to install this on Docker or from source. I'm not going to spend a lot of time during this, as there just isn't time for troubleshooting. If anyone has downloaded it and is having trouble, but everything we do today will be outlined in these tutorials. So let's get started. So a lot of text here, but first thing we need to do is launch our Docker. So hopefully it's visible, make it a little bit bigger. So we do this with a Docker run command where we bind a particular directory, which in this case is on my desktop, a directory I've named docker_geochemfoam 5.2, to a directory inside Docker. And then we tell it that this -it command means that it needs to run interactively. And this is just the name of the container here. If you don't run it interactively, it's going to run really quickly and it's going to shut down. So it's really important to do that. I get some warnings because I'm on a Mac, but you can ignore those, they're not important. Okay,
Ignore
so
warnings at your own peril.
yeah, ignore that we are not on a Linux AMD system. But if you install it on Linux, you will not get that warning. So the very first thing is we want to copy this tutorial into what we call the runs directory. So I'm going to show you here. You can see that I have this on my desktop, and it's now copied in. So it's copied in all of these different files, which will be important in a moment. And so the very first thing we want to do is we want to create the mesh. So I'm going to show you using the vi command. We got a CD in there first. What the create mesh script looks like. So we're going to go through it relatively quickly, but again, there's much more information in this tutorial for you to read on your own if you are struggling. So the image name is Kenton. So this image is actually shipped with GeoChemFoam. It's in this directory, GeoChemFoam images/raw. It is in a raw format, and it is compressed. And this just tells our algorithm whether or not to unpack it, because obviously we don't want GeoChemFoam to ship any bigger than it needs to, so we do compress the images. These are the image dimensions, so how big the image is. And that's important because without knowing this information, GeoChemFoam won't be able to reconstruct the correct volume. Then we put what label are in our images. So this tutorial assumes that you've done some pre-processing. It's not just a raw micro CT image. You have segmented it into what is a pore and what is a solid. And so all this information about the image can be found also in the GeoChemFoam image directory. There's a text file that goes with each of the images that ship that tells you this information. It also tells you the resolution. So this image happens to be 5.3 microns in resolution. But a 512 cubed image is really quite big. And for the purposes of this tutorial, we want it to be fast so that you guys get a sense of what's happening without having to wait, potentially minutes to hours for everything to run. So we're going to crop it. So we crop the image into the first 300 voxels in each direction. And this is where it gets a little complicated. So we have a choice. We could run this image at full resolution, or if in this case Kenton, the grains are really big, the pores are really big, so we don't really lose very much information if we essentially bin the mesh, say 4 or 8 voxels in each direction as one. So that's what we're doing here. So this sets the initial mesh size. So that means that 75 and 300 is 4, right? So we're doing 4 voxels in each direction combined. And then we are setting this N level, so level of refinement. So it starts out on a 75 by 75 mesh, and then anything at the interface between pore and grain is refined. So that means we don't lose, and refined once, right? Because we're doing 4 by 4, we could actually refine twice if we wanted to. But in this case, we're refining once. And then the last thing is to choose a direction, right? For this image, we could run in the X, the Y, or the Z direction. So I've chose 0. In this case, 0 is the X direction. And then, of course, number of processors. And this is quite important depending on which machine you have, because if you leave it at 8 and your machine only has 4, it will not run. So do change this if you are if you have a less powerful machine, or increase it if you have a machine that can do 12, 16, even 64 processors. It'll run faster.
I have a quick question on refinement, if you don't mind.
Yeah.
So basically here, first you downscale then you actually go and refine where you need. So in that process, refine where you need. It's going to the original image, or is it coming up with a refinement on the fly?
I assume it's going to the original image, but maybe Julian understands this better than I do.
So I didn't quite.
So normally, so I have a 300 cube, right? And I go from 300 cube to 75 cube. In that process, I lost some information, right?
Right,
because I take each 4 by 4 by 4 and I replace it with one. Maybe I do a median filter or whatever, one value from that.
No, it's not like that, because what is going to happen before we create the mesh is the image is going to be converted into a STL, right? We have a STL image, and so we have our 75 cell in each direction, and every cell that is crossed by that STL is going to be refined before you start decided which cell you keep and which cell you remove. Right, so you have a mesh that is 75, 75, then it becomes finer. You still have everything, right? And when the refinement has happened, you will then remove all the cells that are in the solid. Right, so if, for example, you're doing n level equal 2 here, so you get to the level of the resolution, the surface area of your STL is the correct one. It has not been downscaled at all.
Changed. Okay. Yeah. All right.
Right. So we're going to run this. So now it's made the STL, as Julian mentioned. It's figured out the value of the pores. And this is a check here to make sure that you haven't forgotten what the value of the pores is and put the wrong value. And it shouldn't take too long to do this.
What is padding the image red by default? Is it padding it the way it's shown in the
so
page
it's not padding the image.
It's just adding one cell in each direction to avoid missing the boundary when we cut.
Yes, but the boundary as you're showing it. Okay.
It will. Sorry, it'll pad with the pore value. That's the answer.
The pore, yeah.
Yeah,
because
yeah.
You're
I see
showing
what you
it
mean.
padding with the pore.
Yeah, yeah.
Otherwise, you wouldn't see that cut surface.
Right.
Yep.
Exactly.
I remember writing that code now. Okay, so it's done. And so we can take a look in pair view. Sorry, I forgot to clear these. So with pair view, we can essentially, it's hard for me to show it to you, but we can drag in what's called, it's a pointer file called PowerView_loader.foam. And so you just drag it in from the folder. And then a few tricky things here. It's going to give you some warnings because it doesn't see anything. That's because for default reasons that I don't understand, PowerView loves to skip 0 time. And then because we haven't reconstructed this case, it is decomposed. So you need to select that. And then if we kind of look at this surface with, or even wireframe,
what?
We can see it's decomposed the mesh into 8 portions, but it hasn't really done anything else. And that's because we need now to snap the mesh to the surface of the STL, right? And so that's what this script run snappy hex mesh is. So I'll just show it to you. Around here. So there's nothing for the user to do. All it does is call snappy hex mesh to snap the mesh. we'll run that in parallel, and then I'll show you what it looks like in pair view once that's done. And then maybe that'll be a bit more clear as to how how refinement works.
And as you're going through this, I can presumably take any image instead, this kitten, adjust the sizes and all that good stuff. And
yep,
run these same steps.
Yep, that's the idea. Yeah. So you can see that's done. So if we refresh,
our homework is writing itself. Right, class? I'll ask AI to quickly write homework for me now.
There it goes. All right, so if we switch to surface with edges, it's slow. Just sort of big mesh. There it goes. Right, so you can see very obviously in the middle of the grain, there's no refinement, whereas near the edges, we've refined once. But if you had chosen twice, you would have seen like right here, these boxes would be divided in 4 or 8 in 3 dimensions. Okay, so the next thing to do is to set up flow. So we have 2 parameters that we can, why this is not loaded. We have 2 parameters that we can change in the initialization of flow, right? It's the delta P, the pressure drop across the system, and the viscosity of the fluid. So in this case, we're running with we fine-tune these for this image to have, a reasonable Reynolds number such that we're not, in the turbulent regime or anything like that for this image. But, if you're running your own image, you would probably want to fine-tune these as you go. And in this case, for the viscosity of the fluid, we've chosen air. So run the case initialization. So you can see case is initialized, and then if we look at run case flow, essentially the only user parameter that you need to worry about is the total time. This is steady state, so the total time should never reach this unless it's having convergence issues. And so GeoChemFoam Docker doesn't give you a lot of feedback on what it's doing fast enough, which I'm not. I could have shown you.
Talk and present and do all of this at the same time. That's all.
Yeah. It's
Let me go debug the code quickly while giving a presentation. Sure.
No. That's not what I'm doing. So tail and simple foam dot out. So you can see it's it's running iterations, and then eventually it converges. In this case, in 338 iterations, and then we can process those flow results very quickly and get our porosity, in this case 13%, permeability. So this is in meters squared. Characteristic length, our Reynolds number, our dosing velocity, and our tau. And so we can then reload again, and our results will appear in and I should also actually point out that in the GeoChemFoam wiki, if you're struggling with ParaView, we do have ways or tutorials on how to check your mesh and how to plot flow streamlines, which I'm going to show you now. So now we have all of these other options. So if we want to look at the velocity, sorry, I realized I've changed the opacity of all of these functions while I was preparing for this, and now I haven't reset them. Right, that's enough. Anyway, so you can see the regions of higher velocity going through the pore throats here. But it's much nicer if we can plot the streamlines. So there's a streamline button here. It's a streamline tracer. It always defaults to a line, which is not really appropriate for what we do with this. So we always change it to a point cloud. And then its radius is always about 10 times too small. So if you delete a 0, you can see it better. And then if we apply it, okay, we've only got 10 streamlines, so this is not really enough. So I usually use 10,000. And we can start to see the flow going through. There we go.
Speaking of defaults, this gray background in ParaView that is a default is a mystery.
It's bad. It's bad.
Why? Anyway.
Yeah. So if you want to crash your computer, you can put 100,000, but you do get a better result. At least you would if your opacity was correct. Julian, you have any idea how to reset this?
What happens if you unclick the enable opacity mapping for surfaces? This unclick it?
Yeah, I did. Second. All right. It's really annoying. Sorry.
There's a way of.
But I mean, we do see the streamlines. Even
Yeah. There you go. That's better.
There we go. It's hilarious, but actually, I think there's a paper on visualization which basically says rainbow coloring, which is default in most software, is the worst choice you can make in terms of giving you the idea of what the range of sizes is, because it's not a strict gradient. It's like all these different colors put together, so you actually can't get the idea how far is something in value from the other things.
Everybody loves it. That's the problem.
Most software, right?
Yeah. Okay, so now we've run flow. We've looked at the permeability and the porosity. So now let's do some transport. So for this, we've set it up to have two essentially arbitrary species. So we have the number of species, what we call them. We just put A and B, but it could be anything: uranium, calcium, whatever you want, and their diffusion coefficient, right? So this is essentially assuming dilute. They're not interacting with each other. They're not reacting. They're just advection diffusion through the volume. So we run the script. So you can see it's decomposing the processors again. And then we'll take a look at the run case. So for this, we've got the total time, the starting time step that you want to start with, and essentially how far out into the future you want to run this, right? We run the transport case. That's run already. and we'll process it. And then if we refresh our stuff again, we'll be able to see the transport through it. So we've got species A. We'll go to the beginning. And we can see species A going through the volume and species B. And they have slightly different rates. So you can see this in the tutorial. There's a much better visualization of the two species here. So A is moving faster than B, which makes sense. Its diffusion coefficient is much larger. And this is the outlet concentration. You can see it's rising through time. So that is all of tutorial 1. So the question is, what should we change? Any volunteers to give a suggestion?
Should I pick a volunteer that can be voluntold?
Can we change the mesh settings?
Thank you, Hyunji.
You want to mesh? Okay. All right. The one that's you've chosen the thing that will take longer. Let's see. Okay. So first thing, when you change anything in the meshing, you need to delete everything you've done. So we delete all. Create mesh.
Do not run this script in a different directory than desired.
So what can we change about the mesh? So how about we we're going to crop it to 200 cubes, but so if we crop it to 200 cubes, we need to change the size of the initial mesh, right? So 50, right? Because it's very important that this number divides evenly into this number, right? Otherwise it's not going to work very well. But we're going to refine twice. This means that the surface will be fully observed.
This is ever so slightly detailed question, but so 0 to 200, is 200 included in that, or is it basically
yeah 0, so it's 0 to 199. We've made it user friendly, but maybe also technically challenging.
Well, Python does the same thing, which
okay. I mean it's all feeds into Python, which is why.
Okay.
So we're gonna, if you want to write something you've changed,
but
it's a little it is. So we're gonna create the mesh. And we'll skip ahead to the straight through to Snappy, just because I don't think you need to see the processor directories again.
So just a quick question. So there are decisions, what is inlet, what is outlet, that are made, and I'm guessing the sides are appropriately labeled. How does one see that, or where is that recorded? What decisions?
Yes,
I can in X, Y, Z direction. What am I doing?
So in a case flow, I think it's
in create mesh.
It's in a create mesh. Okay, yeah. Then you decide which is the inlet and the outlet. It's the direction 0, 1, or 2. And then we have some scripts that copy over that information into all of the different control files.
And can you plot it in some ways? Like if confused, can you go and plot it to yourself?
Sorry, did you plot?
Plot me inlet, outlet.
In
both sides.
In PowerView, you can decide what you're seeing, and at the moment it was internal mesh, and you can choose inlet.
Okay, got it.
It's,
choices.
yeah, here on the left.
Yeah, let me just let me refresh it. Yeah, you can see
Paragraph.
these patches. It won't load because I just overwrote the directories.
Yeah, the entire thing is there. So
It's taking a to refresh.
Is there an option to flip the inlet outlets in a particular case?
No, actually, that's a good point. I never thought about that.
Well, I guess in this particular case, we are doing a pressure drop, so we are not injecting. Right? So it doesn't really matter, like echoes obviously, it doesn't really matter which one is an inlet and outlet for the flow, but for the transport it does. But what you can do is start at 0 and 1, and that basically invert it. Right? It's possible.
bottom line, flip your image, start over.
Yeah,
Yeah.
So you can do each direction, but they always assume that it's in the positive way, which I don't know.
I mean, it doesn't really matter for at least the first part of the tutorial, right? Because you're just doing permeability. It should be the same in either direction.
It doesn't matter if you're doing a pressure drop, but for other test case, we are doing a velocity field, and then that can matter.
Yeah, but solid transport, it can matter. Things get stuck in different ways. Depending which side.
Well, this is a transport of species, so we're not doing particles that can. I don't think it does, right?
That's for sure.
I don't think it. I think it's exactly the inverse, right? I think so, right? It's just advection division equation. If you switch and the streamline are the same, they just reverse, and it's exactly the same transport. Yeah.
It could, though, decide to plot slightly different. I mean, the streamline is a numerical.
Yeah.
That's where you have a starting point, and sometimes you end up in the wall, go back.
But the transport solver doesn't use the streamlines. The streamlines are just a power view thing.
Visual
The transport solver is an advection diffusion volume, finite volume method. It doesn't need the streamlines. Is that the new mesh?
Yep. So this is a new mesh, and you can see we've got really big blocks, medium-sized blocks, and little blocks this time because we did end level 2. But of course, the whole domain is smaller. Okay, so sorry.
How long did that take? Did you ever record?
Like I think it was slightly longer the first time actually, because the domain's actually a bit smaller. Yeah. In the interest of time, let's move on to tutorial 2.
I'm gonna slow you down anyway a bit.
That's okay.
So do you have a piece that integrates and gives the permeability, or is that?
Yeah, so that's the process for a perm, which
okay, so process
would need to run. I would need to run it again, but it is
okay.
We did print it here, right? So when we cat it writes as a CSV file, and with the permeability, that's when you run process flow.
Great.
And it's the same with transport. All of these species get, if you do cat or open these CSV files after process transport, it will give you the concentration with time. Okay. So move on to tutorial 2, which is the fun multi-phase flow one. I assume is everyone here? Is this a petroleum engineering course?
Yes, it is.
Okay, good. I have lots of questions for the students to answer about this.
They should know.
So first we're going to copy it over into our runs directory. So we can see here, micromodel has appeared. Need to CDN again. Right, so much the same as last time. We have the image name, which is included with GeoChemFoam, but you could have a different image if you wanted. It's a raw image, it's compressed, and it's big, right? So we have, it's a 2000 by 2000 voxel micromodel with 10 voxels in the Z direction. And again, we have a solid value of 0 and a poor value of 255. Resolution is quite large, it's 30 microns. And we're going to crop the middle of this image. So in this case, we're cropping from 700 to 1300. So it's a 600 by 600 by 5 micromodel, maybe 6. Now I'm confused, given Masha's question. So number of cells in the initial mesh, so 300 by 300. So that's half of what it is that we've cropped. And we're doing N level 1. So it will refine the interfaces to be exact. Direction of flow is still in the X direction. And this is important for permeability calculations. So we want to not include essentially parts of the image that are near the edge because of capillary end effects. So when we do our calculation for relative permeability. The reason it's slightly more cut on the X than the Y is because we don't start the injection from the boundary because that causes some numerical instabilities. We start from about a quarter of the way through, so we don't want to include that first quarter in the calculation. So we'll create the mesh. And you can see in this image, there are a lot of other values that are not 0 and 255. So our scripts just cut it in the middle between them, separating poor from grain. And those values are just because the image was, created with Python and interpolated around the edges. So there's some voxels that were kind of between 0 and 255 that became gradients, essentially. And we're going to run Snappy, because I don't think you guys need to see the processor discretization again. While that runs, we will set up our pair view. So let's run. Oh, pair view keeps running. Go ahead and delete this one so that we don't get confused.
And where are you running all of these simulations?
This is on my laptop.
Okay, so it is a laptop.
It is a laptop, yeah. It's a good laptop, but it's a laptop. So if we look surface with edges, again, the mesh. Because you're only seeing, so we've essentially compounded the Z completely. So there's only one cell in the Z direction. And that's automatic in this tutorial.
That's a 2D, essentially.
So it's become a sort of 2D.
Quasi, whatever, yeah.
Quasi, whatever, yeah.
Quasi 2D or quasi 3D. I don't know how you want to look at that.
No, it's a 2D finite volume system. Where the boundary at the top and the bottom don't exist here. But when you calculate, there is a volume of the cell. But the boundary on the front and back don't exist.
Does it account for the boundary conditions, like no slip condition?
So I think we're gonna see that. So we had no slip condition before in the 3D. For the flow, we still have no slip condition. There's also gonna be a contact angle that's coming in a few minutes.
So if we
it's no slip for the flow on the solid walls.
So if we open the inner case, we're setting a flow rate. This is the total injection flow rate. So the way that this simulation works, first you have to solve the single phase flow, and then you add the multi-phase flow, and you solve that. So first we're going to do the single phase flow. So we've got the viscosity of the water and the flow rate. We initialize the case, and then we define the total time to run. So this is completely identical to what we were doing with the Keton tutorial. Right, and process it, right? So we cat. Yep. So now we have the porosity and the permeability of the micromodel, and here's where we can fine tune a Reynolds number and Darcy velocity as needed.
Note the very high Reynolds number. 5, which means that the permeability is probably not quite accurate because we just saw it 5. If we interested in permeability, we'll do it at a much lower flow rate. We will rerun this during the flow rate. The problem is we want this to be fast, and multi-phase flow take a long time. So ignore the fact that the results are not quite right here, so that we can just run this in 5 minutes rather than in a few hours, right? If you want to do this properly, divide the flow rate by 100.
We have committed such crimes before.
Right, so then we're going to look at the two-phase flow in its script, right? So total flow rate, now we have 2 phases, right? We've got one is the resident phase, and the other is the phase that will be injected. So those are sort of essentially what this is going to initialize as look like in the initial time step. So as I said, 25% will be filled with the invading phase already to avoid these weird boundary effects. And then you have your fluid densities and viscosities, your interfacial tension, and your contact angle. Well, so we run that, you can see it's setting the alpha field. So that's what this means. Like if it's alpha is between 0 and 1, with 1 being water and 0 being your invading fluid. Okay. And then again, we set our total time, our write time step, and our run time step. I think this will take a minute or 2.
So you saw in the 2 cases, there's a single phase and 2 phase, the flow rate were the same. It's not necessary, but the permeability is calculated with the first flow rate. So when you calculate rel perm, it will use the previous permeability. So if you use a different flow rate, this might be different, and this might get you rel perm that are more than 1, for example. So it's possible, but it's not ideal to use different flow rate for single phase and multi-phase.
Yeah, and you can see it's running now, and we're doing okay. Does anybody maybe want to hazard a guess as to what would happen if the current number went over 1? Does anyone know what a current number is? No?
You'll get a whole bunch of not numbers.
Yeah. So this is what controls our time step. It's what makes multi-phase flow so hard, right?
Okay. Those of you who have been in the program longer Hami has to go through that in his course, does he? Quran numbers, stability of hyperbolic systems. Yes? Bernie, is that a yes?
I mean, he should.
Have you taken the course or no?
No, I haven't.
Mateos, have you taken the course?
I think I've seen his notes that he has. But Mateo's probably
Yes, but we didn't discuss about stability of hyperbolic yet.
Okay. So maybe they know, maybe they don't.
Okay.
I guess what that roughly means your numerical method shouldn't run faster than the process itself because it's going to get unphysical. How's that?
Yeah. So
Okay. Multi-phase flow is even much more complicated. That if it was just the Courant number, we'll be happy.
Agreed.
yeah. There's also Bractal, right? So there's
so
So
much.
while we are waiting, what are you calling a good laptop? That means so we can have an idea.
it's an M4 Max 128.
So 128 gigabytes of memory.
Yeah, but you wouldn't need that to run this.
Okay.
But I think I've got 12 performance cores and 4 efficiency, so I could be running these faster, I guess.
Okay.
I have one question.
Yeah, just go ahead.
Yes. We just initialize like this, like 25%. But what if we want to run the simulation after like drainage and then imbibition?
Yeah. So you go ahead, Julian.
I mean, if you're not interested in a drainage helper, then that's a brilliant idea. Now, of course, this will take a long time, right? Having a drainage up to irreducible water saturation is going to take hours of simulation, right? So the tutorial is just here. It needs to be run in a few minutes, right? Otherwise, that's not really a tutorial. But so if you're using this to produce real permeability in a real image, you definitely want to do what you just say and run this tutorial up to the end of drainage and then restart to do imbibition from that point. It's not automatically done by the tutorial because we can't run full drainage in, not hours.
Right.
So you're going to have to work a little bit harder if you want to do that. But this is the right idea.
So I have a question. Would it be useful or stable if that blue ribbon of 25% of the image, if I just created a small reservoir or like a flat portion porosity one at the beginning?
Not as good as having,
I call that the reservoir. I used to do that with the level set stuff. Like I just add and I can prescribe how many
don't you
to add at the beginning to have that
numerical effect at the connection between your pad and your beads, that recirculation around there and something like that. When we put a big reservoir,
okay.
In this case, that's what will happen. You will start having some strange flow at the connection between your reservoir. The thing that I want to do, but it will take a bit of time and is to include that injection zone with different tube, the kind of spider one.
Mm-hmm.
The spider one.
What models often do. Yeah. Okay.
That would be the best way of modeling this. Now the problem, of course, is you're just gonna have a lot more cells too, and it's already slow.
Sure.
Right. Multi-phase it's hard. Right. If you see what you've done with single phase, it took a few minutes when you do a real image. This is a micro model, and it takes a long time because it's hard. So you're gonna want to save as much computational time as you can anywhere you can.
Right.
And there we go. So this is what we've run in 5 minutes, 0.1 seconds of multi-phase flow. And if you look at the relperm.csv after you've done your process, two-phase flow, you'll see it prints the relperm of the area between the 25% and 5% before the end. All right. Should we run? We've got 15 minutes left.
The script writes a capillary number too.
Yes, it does write the capillary number.
But you have a capillary number for each phase, which is the average of the velocity in each phase, of each phase, CA1, CA2 here, right? So capillary number 1 image 3 in the phase 1 and 1 image 2 in the one. So it's high capillary numbers. That's why it's almost like straight line here. It's very high capillary, very viscous relperm.
I have one question about this.
Yep.
Are we applying the body force or injecting fluid into this?
We're
Like
injecting.
Injecting.
I don't know what you mean by body force.
Like to make the flow happen, there should be a force or like injection or
It's
pressure
it's
difference,
constant
or-
flow. It's not constant pressure.
Can you do this for multi-phase, the body force? I know this for single phase, but for multi-phase, can you do a body force? Then, I guess you would put 10% of saturation in there, do a body force, and have a recirculation, right? That's what you have in mind with your body force.
Yeah.
Yeah.
Well, we just went through Lattice-Boltzmann, and Lattice-Boltzmann you can include a body force. But here you have a gradient of pressure in actual simulation.
If you're doing a body force, do you need to have a periodic system? Because everything that's go out must be gradient, right? You need to have a periodic system.
Right.
A bit more complicated. Right? So not in this case, we're injecting. It would be nice to be able to do body force, but again, it's going to make the system bigger, and we want it to be fast.
Thank you.
Okay, so we've got only 15 minutes left. Should we move on to tutorial 3, or do we want to change something in tutorial 2? Any?
So we do an audience. Choose how to end this demo.
Otherwise, I will choose for you.
Who wants to move to a different problem? Raise your hand or make some noise. Or
Okay. Our one voting
I
member.
think
has
everybody's
chosen.
sleeping behind, other than Hyunji and
All right,
Bernie are
let's do
awake,
it.
and everybody else. Okay, Evgeny's awake. Okay.
All right, tutorial 3. So sorry, Julian, I forgot to share
There we go.
your slides for this.
People are proving they're awake. Okay. So move on
Alright.
to a different problem. All right.
Move on to a different problem. So let's see if. Right.
Yes.
So we go to Estiolatus. So this is Estiolatus. It's a French formation of carbonate. And it has what we call microporosity. So parts of the rock that are not pore, not solid, but under resolved porosity. So little pores that are too small for us to see. So this is a different way of solving flow. It's using a Brinkman type formulation that we can then use to calculate permeability. And this is an important step beyond standard pore scale flow, because in many real rocks, not all porosity is cleanly resolved or fully connected at the imaging resolution. So we can represent these unresolved porous regions through effective properties. And in the governing equations, Darcy resistance and effective viscosity are key terms because they allow us to model allow the model to represent flow through regions that behave more like a porous continuum than a fully resolved free fluid space. So we will go to tutorial 3.
All right. And if
want
you
to
want
create
to see original images of the there is at least 2 on the portal. So just
there are a couple packages with
popular.
GeoChemFoam.
It's popular.
So I'm actually going to skip ahead to the demonstration that I had planned for the second part of this, which is we're not going to do 3 phases. We're going to do 5 phases. So pore, solid, and 3 phases of microporosity. All right. So same as last time with the image name, which I've just changed to 5 phase. We've got the dimensions. We need to tell the model which phases are pore and which phases are solid, and then the label. So I believe in this one, the solid value is 5. And we've got 5 different phases. And we need to assign a porosity to some of these phases. So obviously, if it's pore, the value of the porosity is 1. And if it's solid, you'd think it would be 0, but because we're using the Brinkman formulation, we have to have some little amount of porosity. Otherwise, we get divide by 0 errors in the solver. It's not a problem that we have tried to address, but have not yet been 100% successful at. And then in between these different phases of microporosity, now these could be different chemical phases, they could be phases with slightly different heterogeneity, but this is a very common problem where the phases of microporosity have different porosities. Then, as we did before, we define our cropping parameters. So we're going to crop a little 200 cubed bit of this image. And we can assign a pad width. The default is 4. And we need a pad, obviously, because we can't inject into a solid phase. So on each side of the image, we put 4 voxels that are essentially pore, so that when we push fluid through, we don't encounter immediately a solid and cause some instabilities. This image is a resolution of 4 microns, and it has 50 cells in the initial mesh, which we will then refine twice. We also, because of the Brinkman formulation, we do need to do a little bit of smoothing. So this is how thick the smoothing layer is here. Layer equals 2. Is that right, Julian? I think it is. And then whether or not we refine the Stokes phase, because you could refine the pore space as well as the grains. And then this is a flag, because we have some tutorials that use this solver with a 2D image, but this is a 3D image. Again, the flow is in the X direction, and we split it into 8 processors, 2 in every direction, so 2 to the 3rd power. Oops. So if I run create mesh, be able to see it's creating all of these.
The script is different from the previous one because we're not using SnappyX mesh.
Yep. Yeah, so we'll go straight to init case flow from here. We won't do Snappy, because one of the wonderful things about DBS on a Cartesian mesh is you do not need to snap it, which means you're not limited by that particular utility, which becomes unstable after about 600 cubed.
Can you show the mesh before you do in case.
Yeah, I will. Right. So, like to pair view, drag in our pair view loader, again decomposed. And there it is. So X is local porosity. So that's what I'm plotting here. And so you can see our pads are 4 voxels on each side. And then the red is pores. And then we have multiple gradients of microporosity. And then the blue is solid. So if we go to in a case flow, yes. Now we have a couple of different options. So as we were, I got a typo there. As we were sort of talking before, in this case, you can choose whether you have a boundary of flow or pressure. In this case, we've chosen pressure. And we've got a flow rate of 0 because we have a pressure drop. Now, if we wanted to do a flow rate instead as a boundary, we'd switch these around. We'd have a flow rate and a pressure drop of 0. And then we have the fluid viscosity. This is the viscosity of water. And there are 2 options here. So for the model type, we can do it just on a grayscale image, no segmentation at all. Or we can choose to do phases. So if we've done some image analysis on this image, this is often the case, we've segmented the pores. We have approximately some idea of what the microporosity, is it all 1 phase? Is it 2 phases? Is it 12 phases? So we have in this case, we've segmented it into 5 phases. Because remember, we've changed the image from the base tutorial. And we have the porosity of each phase, which I hope I'm remembering correctly what I did. And then permeability. And so this is where we can decide either to assign that permeability ourselves or use Kozenik-Karman. So Kozenik-Karman equation is essentially you assume that the porosity is evenly packed elliptical beads, and then there's an equation which equates the permeability to porosity.
So does it assume certain grain size within a porosity, or what does it do?
When it's evenly packed elliptical beads, I think there is an assumption of grain size.
It just assumes the same grain size everywhere.
It's just under your cursor, you give the constant, right?
Okay.
Yeah.
For the Kozenik-Karman, so we're assuming that everything is the same except the porosity, and we give a constant that is probably fitted in some way to get the best result, right?
So now I'm just putting in values for the other 2 phases of microporosity. So I'm essentially assuming, we have data for this, which you could use. It is in the text files associated with the images, but I've just made it up here where I'm assuming that if it's 25% porosity, it's probably got a lower permeability than something that's 45% porosity.
If you just throw a grayscale image at it, like usual one, so 0 values between 0 and 255 and anywhere in between, how stable is that?
I think you're going to really struggle if you don't at least segment the pores, because then they're going to be, unless it's a very good image, you're really going to struggle to have them not be assigned as Darcy values, right? But apart from that, it would be.
That's what I thought. Because also, even if you filtered the noise, the moment you have a range, I would assume it would struggle a little bit.
Well, actually, if you have a segmented image that is just 0 and 1,
sure,
you have a very sharp. But no, because you have a very sharp interface between pore and solid, for which you have no permeability and a huge permeability. And this is not real, right? The segmentation is just done because you decided which is a pore you created like this roughness. And actually, it's better to smooth it.
Okay.
It's better to smooth it. You get a better permeability if you just smooth it a bit. So if you have a grayscale image with a very good filter, right? If you filtered it in a very good way, that's probably the best image we can have here. The pore will be like smooth at the right resolution, right? So I would like, and I think very often, you have this stage where the filter is perfect and people just segment it into phase to give us that, and I want to see the one before.
And it's struggling with the sharp transitions.
The sharp transition.
As long as you smooth the transition.
Yeah.
Okay.
Yeah. Brakeman is struggling with this, because of this division by zero, we have to put a tiny bit of which means the pressure and the velocity will get to zero inside the solid, but the pressure is nonsense.
Okay.
And that could create some problem when it's sharp.
Okay, so I've run case flow. There was nothing really to change. There's just a total time in the run case flow script. And process flow. While that's running, we'll do a refresh on this. So, got some velocity. Now it's a bit hard to see because everything's meshed in this image. It's not like the previous example where we could see the pores. So it's a bit better to run streamlines on it. So we'll run point cloud, take out at 0, and do. Let's try 10,000 first and see how we get on. It always goes back to pressure. Ice. There you go. So we can see turbo. There we go. So we can see that flow is quite tortuous through the main flow paths of this image, but there is still quite a bit of flow connecting some of the microporous regions. And with that, I think we're out of time. So thank you all for your attention, and I hope you've learned something about modeling in GeoChemFoam, and yeah, let us know if you end up using our solvers.
All right. Well, thank you very much. Kind of dominated the questions, so I apologize for that. Any parting questions?
Can we also model diffusion with multi-phase flow?
Yeah, what type of
How much
diffusion?
time do you have?
Yeah. I mean, yeah, we have multi-phase flow solvers that also do chemistry, if that's what you mean.
So like hydrogen and brine, and then like hydrogen can diffuse into water.
Yeah, so I've done those simulations before. You can do it.
Okay.
There is a tutorial. Which one is it? There's a tutorial which is not hydrogen and water, but it's two phase. We look at the wiki. We can point it. It's
Is this multi-phase reactive transport into greenstone?
This one with reaction. Yeah, 11 is good for this. But so here this is.
So you can see the species diffusing.
But in this particular example, the interface is blocked, but you can change it. But because this is oil and water, and H+ is not going inside the oil, but there's a parameter that you choose, which is put at 0 now, and if you don't put it to 0, it will go into water, which is what you want to do. So you want to look at this tutorial.
Thank you.
Is the container set up for multi-node running or just single node multiprocessor?
There is a singularity version of 5.1. We haven't set it up to run on 5.2, but as far as I understand, turning it into something for Slurm supercomputer is relatively straightforward. But in terms of if you compile it from source, you can definitely run it on the supercomputer. And we've run, I don't know, what's the biggest image we did, Julian? Like 2,000 by 2,000 by 10,000, something huge.
Yeah. 40 billion cell.
So that we obviously needed a supercomputer for.
Yeah, we were talking about putting it on your supercomputer, Marshall?
Yeah. So we do have supercomputer access. That's where the portal is hosted. So we right now, Bernie is the main architect of setting up a lattice Boltzmann or adding it as something that you can navigate to from the portal and set up the simulation, which is basically setting up the job scripts and then sending it to the parallel.
Yeah, so I mean, there's a guide to using GeoChemFoam on Archer 2. And if you follow through the documentation, there is also documentation on the Archer 2 website, which kind of went through like what was in the setup of it.
Archer 2 is a UK national supercomputer.
Yeah, sorry, that was missing from my explanation. Which is, like very small compared to the supercomputers of the US, but
Texas, so they're called Lone Star, Ranger.
Okay, yeah, I mean, this is like 5,000 nodes or something, but yeah, it does the job.
But now, if you want to make a singularity container for GeoChemFoam 5.2, and if you're happy to share it, we'll put it on the website and mention you as a collaborator. We'll be very happy for that. It's not something we use because with our supercomputer we go with native installation, but it is useful for the community. So if something you want to do, we'll be very happy to.
I mean, that being said, if you've already got OpenFoam 2512 installed, it's very easy to compile GeoChemFoam from there.
But more option.
On Lone Star 6, there is OpenFoam. I don't know now which version, but there's one sitting there pre-compiled because it's widely used at the university. So it would be it's potential. I'm gonna bite my tongue if I say that it's potentially easy, and I'm gonna eat my words.
The problem is that there is 60,000 versions of OpenFoam, right?
Yeah. Yeah, so we use 2212 for this version. Next version it'll be 2512, I think, at least.
There's more than that. Version. So I think in Archer 2 they probably have something like 12 versions of OpenFoam, and we've run only with a few of them. It's installing it when it's not the version we've done could be a little bit more involved.
Right.
But
so I mean, there are two pieces to it. I'm pretty sure that we can figure out just the compilation of GeoChemFoam on, say, Lone Star 6 or one of these machines. But the piece, I'm interested in connecting it to the portal too, and that's a little bit more involved. So now we're waiting to at least have one running example of a HPC application, because right now we have Jupyter notebooks working on the data. But basically one example of, and once we have that worked out, then others should follow in a relatively straightforward manner. Because there's like a web script you know, the web forms that are filling out and setting up the scripts, because that's all supposedly running through browser.
Yeah, when you run thing on supercomputer, you want to run the last test case that we've done, because the meshing, because it's so simple, is done all in parallel. Where the previous mesh is not everything is in
Okay.
parallel, so that we struggle on big images. You don't care, you want to do a 500 cubes, that will work, but we were saying 2,000 by 2,000 by 10,000, it has to be this way, this tutorial. And
Right, okay.
we run it on.
So each voxel is its own
Yeah.
element.
No.
Done.
No. Don't do that.
Yeah. No snapping
Well,
anything onto anything else. Okay. All right. Well, thank you so much.
Thanks for the
See you
invitation.
in person sometime soon this summer.
Hope so.
All right. Thank you. Bye.
Thank you very much.
Thank you, everyone.